So here we're looking at some additional identities to add to our collection from our previous study. So previously we had the 4 sets of identities: the reciprocal identities, the quotient identities, so we could rewrite tangent and cotangent in terms of sines and cosines. We had the Pythagorean identities, which allowed us to increase and decrease the number of terms in an expression. And then finally, the relatively unused ones were the cofunction identities. So here we're expanding our set of possible identities, tools in the toolbox, to the sum and difference formulas. So you can see that there's the sine, cosine, and tangent versions of each one of these, where it's the sine of alpha plus beta. So alpha is one angle, beta is a second angle. So if we have the sum of 2 angles that we're taking the sine of, we can find it by expanding into the expression that you see in front of you. Or if it's the difference of the 2 angles, angle alpha minus angle beta, you've got the expression there that you can see. And so we've got the same, or different formulas for cosine, and then of course you can see the different formulas for tangent. So the key thing to understand is sine, when we say sine of alpha plus beta, or sine, sine of the sum of these 2 angles, or the difference, it's not sine times what's inside the parentheses. It's not a distributive property situation where I take the sine of alpha and then the sine of beta, and then I just add those 2 results together. That's not the way it works. It's sine of the angle. It's a function. And so it's not a distributive property situation, and that's why it doesn't end up working out to just be sine of alpha plus the sine of beta, or sine of alpha minus the sine of beta. You can see that we have these more complicated expressions that we have to make use of. The main purpose of these formulas is to expand the universe of angles for which we can use the unit circle to find exact values of the sine and cosine and tangent ratios. So with the unit circle, we're restricted to just the 30, 60, 90 triangles, the 45, 45, 90 triangles. And so instead now we're going to be able to expand that universe. So it may be useful for you going forward to have a unit circle out in front of you to help you with what we're going to do in the examples coming up next. So in the 2 examples that we see here, we're asked to take the cosine and then later the tangent of 2 angles that are definitely not on the unit circle. 75 degrees is not a unit circle angle. Negative 105 degrees is not a unit circle angle. But what we can do is we can rewrite 75 degrees as the sum of 2 angles that are on the unit circle. And so if we think of 75 degrees, instead of just being 75, but as being 30 plus 45, now 30 degrees is a unit circle angle, 45 degrees is a unit circle angle. And so we can apply that sum formula for cosine up above and use that to expand the expression that will be in terms of only cosines and sines of these 2 unit circle angles, 30 degrees and 45 degrees, which means we'll be able to find the exact value. And so if we look up above on the page, you can see that the formula expands out into cosine of 30. So this serves as our alpha, this serves as our beta. So cosine of 30 times the cosine of 45 minus the sine of 30 times the sine of 45. And so now these are all expressions that we can use our unit circle for. So the cosine of 30 is root 3 over 2. The cosine of 45 is root 2 over 2 minus the sine of 30 is 1/2, and the sine of 45 is root 2 over 2. And so now if we just kind of clean up here, root 3 times root 2 is root 6 over 4 minus 1 times root 2 is root 2 over 4, or a little bit cleaner way to write our answer here is root 6 minus root 2 all over 4. And so here we have an exact answer. We didn't have to push buttons on our calculator, we didn't have to round off any decimals, but we were able to find an exact answer for an angle that is not a unit circle angle, but is instead using the formula found using unit circle angles to get that exact answer. For the next one, for tangent of negative 105 degrees, we need to do the same thing. We have to somehow rethink how we can create negative 105 by either adding or, as we'll see here, subtracting two angles that are on the unit circle. And so in the case of negative 105 degrees, if we want to think that through, we can say it's going to be tangent of 30 minus 135. So again, 30 degrees is a unit circle angle, 135 degrees is a unit circle angle, and so we can use these two as our alpha and our beta in our formula for the tangent of the difference of two angles. Now, unfortunately for this one, we're going to have quite a bit of simplifying that we're going to have to do as we work our way through this. So bear with me as we go through this example. But the first thing we've got to do is we have to expand the expression using the formula up above. So using the difference formula for tangent, it's tangent of 30 minus the tangent of 135 up top over the 1 plus the tangent of 30 times the tangent of 135. And so again, these are unit circle angles, so we can use our unit circle to find what these various tangent ratios are. So tangent of 30 is root 3 over 3 minus the tangent of 135, so that's in the second quadrant, so that's going to be negative 1 over 1 plus, and now it's the same values, tangent of 30 is root 3 over 3 times tangent of 135 is negative 1. And so we do have a lot of simplifying that we have to get through. So let's get started on that. So we've got root 3 over 3 plus 1 on the top, since we're subtracting a negative, over, and then it's 1 plus, try that again, 1 minus root 3 over 3 on the bottom. So we have a couple issues that are going on here. First of all, we've got fractions within fractions. So we're going to have to deal with the fact that we have a complex fraction, and we can't have a square root in the denominator. So the first thing that I'm going to recommend is to get rid of the fractions within the fractions. And the trick that we can use here is we can multiply the top and bottom of our fraction by 3. And so if we distribute that to the top and distribute that to the bottom, hopefully we can see where that leads. 3 times root 3 over 3 leaves us with just root 3. And then 3 times 1 gives us 3. So now we don't have a fraction within a fraction in the top, and the same thing is going to happen on the bottom. We're going to end up with 3 minus root 3 on the bottom. So we dealt with the first issue of having a fraction within a fraction, but now we have the problem of having a square root in the denominator. Now we can't just multiply the top and bottom by root 3. We're going to have to multiply the top and bottom by the conjugate pair, so by 3 plus root 3 on the top and bottom. And so again, I'm going to keep on sliding over here as we work our way through this. So up on the top, we have to do the full FOIL. So we can say we're going to end up with a root 3 times 3. We're going to end up with another root 3 times 3. So we're going to get a 6 root 3 when we add those together. Then we're going to multiply the 3 times 3, which gives us 9. And then we're going to multiply the root 3 times root 3, which is going to give us 3. So I'm just making sure to multiply through my full FOIL. On the bottom, we have a difference of squares situation. That's the whole idea behind the conjugate pair. So we just have to multiply the firsts. So 3 times 3 is 9. And we have to multiply the lasts. Negative root 3 times positive root 3 is a negative 3. So up on the top, we can add together the 9 and 3, so we get 6 root 3 plus 12. On the bottom, we can subtract 9 minus 3 is 6. And so now we can see the finish line. The last thing we've got to do is to simplify. And so I can divide everything by 6. I can't just reduce the 6's here. I have to be able to divide into both pieces. So indeed, those 6's will cancel out, but I also need to divide the 12 by 6 to get 2. And so then our final answer on this one is root 3 plus 2, or usually we would write it 2 plus root 3. So I know that's kind of a long and drawn out process with a lot of simplifying and rationalizing that has to happen, but that generally only happens on the tangent questions. For the sine and cosine questions, you will pretty much always end up with an answer that involves a root 6 and a root 2 up in the top. One of them will be positive, one will be negative. They'll both be positive or they'll both be negative, but some combination of root 6 and root 2 on the top, and then a 4 on the bottom.